Dear students, this is lecture 7 revision for the Foundation Advanced course, and in this video we will be talking about fluids. First of all, we'll talk about pressure. Pressure inside the fluids. You see these molecules moving inside fluid, right? These are the molecules that are moving inside the fluids. These fluid molecules collide with the walls of the container, and because of that collision, a force is developed. As the number of collisions is very high, there is a constant force that is acting on the walls of the container. This constant force generates pressure on the walls of the container, and let's say if you keep something, let's say you keep something, a surface like this. On this surface also, the fluid molecules are colliding. Due to that collision of fluid molecules with the surface, or this surface will also feel a force in the direction which is opposite to the collision, right? On the right part of the container, this part of the container, because fluid molecules are coming in this direction and hitting the surface, the direction of force that will be acting on this surface will be towards the left, correct? So pressure is there because of the force acting on the walls of container due to collision of liquid molecules. Due to this constant force, a pressure is generated in the fluids. Okay. Now let's move on to the next slide. In this slide we are going to define pressure. Pressure is defined as the force perpendicular to the area divided by area. So basically pressure is perpendicular force acting on the surface per unit area. Unit of pressure is pascals. 1 Pascal is the pressure when 1 Newton of force is acting on 1 meter square area. Other units of pressure are atm, atmosphere, and torr. Basically, atmosphere is the atmospheric pressure. It is equal to 1.01 into 10 raised to power 5 Pascal, or there is another unit as well which is known as bar. Okay, 1 bar is equal to 10 raised to power 5 Pascals. Torr is another unit of pressure, and 1 torr is equal to the pressure generated by 1 mm of Hg. This is equal to 1 torr. Now remember that pressure is a scalar quantity. Force is a vector quantity, but pressure is a scalar quantity. Also the area is a vector quantity. So basically force perpendicular to the area is equal to pressure into area, where pressure is a scalar quantity and area is a vector quantity. Now let's move on to the next slide. In this slide we are going to see the pressure difference at a depth of liquid. So let's say you have liquid contained in this container. Now let's say the pressure at this point is 0. So the pressure here at the bottom or at the depth h is going to be equal to rho g h. So let's say you have a container like this and it is filled with some liquid and the density of liquid is rho. There are 2 points, let's say this point is A and this another point, let's say this point is B, and there is a difference of depth d between these points. Then the difference in pressure between points A and B is going to be Pb minus Pa is equal to rho g h. Now if point A is at the atmospheric level, let's say your point A, which is like this, so this is the container, this is point A which is at the atmospheric level, and this is point B and this is point B. So for the pressure difference between these 2 points, Pb minus Pa is equal to rho gh. Okay, now thus P is equal to PATM because it is open to the air, so PA is also equal to PATM. Okay, so PB can be written as PB minus PATM, which is equal to rho GH. Now this term PB minus PATM, this is known as gauge pressure. Okay, so this is known as gauge pressure. Okay students, now let's move on to the next slide. Okay students, now we are going to solve this problem. The problem is find the pressure at the bottom of a chair with 4 legs. When a person of mass 60 kg is sitting on the chair, the mass of the chair is 2.8 kg and the radius of the bottom is 1 cm. Okay, now let's make a free body diagram here. Okay, so for the free body diagram, this is the ground, and there is this object which is sitting there. It is a chair. So the downward forces which is acting is equal to the weight of the chair, and there's an upward force which is the normal force, correct? So that total force is the weight of the chair and the person. So the weight is equal to weight, which is equal to W, is equal to the weight of the chair and the person. So it is equal to 60 plus 2.8 and multiply this by G. Okay, multiply this by G. Let's take the value of G as 10. So the total force is equal to 60 plus 2.8 into 10, which is 628 newtons. Now the total area is equal to the area of 4 legs. Each leg is circular, so the total area is 4 times area of each leg. Each leg has an area pi into, as you know, the radius is 1 centimeter. When we convert this radius of 1 centimeter to meters, it will come out as 0.01 meters. So the area is 4 pi into 0.01 square, correct? So basically this is equal to 4 pi into 10 raised to power minus 4 meter square. Now as we know that pressure is equal to force acting perpendicular to the area upon area. Now this whole force is acting perpendicular to the legs. So the pressure is going to be force, this W, divided by area. Weight, as you know, is 628 divided by area, which is 4 pi into 10 raised to power minus 4. Now let's solve this. After we solve this, we get the answer as 5 into 10 raised to power 4 Newton per meter square, or the pressure is equal to 5 into 10 raised to power 4 pascals. Okay, so this is the pressure at the bottom of the legs. Now let's move on to the next question. In the second question, in an open container, the water is filled up to a height of 1.5 meters. We have to find out the pressure at 1 meter depth of water. So the container is open. So the situation looks something like this. The container is open, and here the pressure which is there is the atmospheric pressure. And we want to find out pressure at this point. This point is at depth 1 meter, correct? The density of water rho is equal to 1000 kilogram per meter cube. We are going to take the value of G as 10 meter per second square, and the depth of the water, as you see, depth is equal to 1 meter. Atmospheric pressure, as we already know, the value of atmospheric pressure is 1.01 into 10 raised to power 5 pascals. Now using the formula for pressure difference, let's say the pressure at A is equal to PA minus PATM is equal to rho G D, correct? Now PA, I have to find it out, minus the atmospheric pressure is equal to rho, the value of rho is 1000, into G, which is 10, into depth, which is 1 meter. So PA is coming out as 1.01 into 10 raised to power 5 plus 1 into 10 raised to power 4, which is equal to 1.11 into 10 raised to power 5 Pascal. So the pressure at point A is equal to 1.11 into 10 raised to power 5 Pascals. Okay students, so that is it. In this problem we have found out the pressure at point A. Now let's move on to the next one. Now we are going to discuss about buoyancy. We know that if you submerge something in water, it feels lighter. Some things can float in the water and some things cannot flow in the water, but all of them feels lighter inside water. It is also able for us to swim in water. It is possible because of the buoyant force that acts on us, and the tendency of applying that force is known as buoyancy. Now first of all, what we are going to learn about is the volume of displaced liquid. Let's say you had a container which is filled to the water up to the brim and there was no rock inside it. Now what you do, you bring a rock and you insert that rock inside the water like this, and some of the water will flow out, correct? This volume of water which is coming out is equal to the displaced water. Now this volume of displaced water is going to be equal to the volume of this rock, because the rock is completely inside the water. The volume of rock is equal to the volume of fluid displaced. Okay, and as we talked about buoyancy, the tendency of liquids to apply an upward force on the object submerged inside the liquid is called buoyancy. In this slide, we are going to talk about buoyant force. You have seen ships floating in water, right? They are able to float because of buoyant force. Water acts an upward force known as buoyant force on these objects and they float in water. So basically what happens is when something is floating, then weight and buoyant force are equal to each other. But when the weight is larger than the buoyant force, the object is going to sink. Now, because of this buoyant force, we feel lighter in water, we are able to swim. Ships are also floating in water because of this buoyant force only. We will be discussing about the magnitude and strength of this buoyant force in the next part. So I will see you guys in the next video.